Here are the top 10 things you must know about functions. Must know number 1. What is a function? A function is a relationship between two variables where each input corresponds to exactly one output. And to help you understand this definition, let me give you an example of a relationship that is a function, such as y equals 2x squared minus 5, and a relationship that is not a function, such as x equals y squared. Both of these equations show the relationship between the variables x and y. But relationships can be shown not just in equations. We could also make a table or draw a graph that shows the relationship. And from those tables and graphs, we'll be able to more clearly tell why this one is a function, but this one is not. So let me make a table of values for both of these. For y equals 2x squared minus 5, I'll pick x values between -2 and 2, and then I could take all of these x values and use those as inputs into my equation for x, and then do the calculation 2x squared minus 5 to get the output value of y. And because it's able to output these single values for y for each of these input values x, we know that this relationship y equals 2x squared minus 5 is a function. And I'll plot all of these points to get a rough sketch of its graph as well. And now for the relationship x equals y squared, let me make a table of values. And then because x is isolated, it would actually be easier to choose values for y and then calculate x. So I'll choose y values between -2 and 2, and then the equation tells me the x values are equal to the y values squared. So I'll just square all of these y values to get the x values. And then if we use this table of values to look at the relationship between x and y, I notice that when x is 4, y could be either -2 or +2. So there are two different y values for the same x value. So when x is 4, it's able to output two different values, both -2 and 2. That's why this is not a function. And let me show you what the graph of this looks like by plotting all of those points. And now that we have the graphs of both of these relationships, I'm going to show you a really easy way to tell from the graph if a relationship is a function or not. It's something called the vertical line test. If any vertical line touches a graph more than once, the graph is not a function. So if I look at this graph of the relationship x equals y squared, it should be obvious that this is not a function because it would fail the vertical line test. For example, if I drew a vertical line through x equals 4, you could see it touches the graph of this relationship in two different spots. If any vertical line you can draw touches the relationship in more than one spot, it's not a function. It fails the vertical line test, right? This demonstrates that when x is 4, y can be both 2 and -2. There are two different output values, y, for the same input value, x. But if we look at the graph of the relationship y equals 2x squared minus 5, which is a function, there is no vertical line I could draw anywhere that would touch this relationship in more than one spot. Any vertical line I draw would just touch the relationship in one spot. For example, a vertical line drawn at x equals 1 would just touch the relationship right down here at a y value of -3. And before I move on to the last section, I actually want to take a second and show you a notation we use when we have a function. So for this function, y equals 2x squared minus 5, we actually don't write y. We want to actually give this function a name. And by convention, it's most typical to use the letter f to name the function. So function notation looks like this. Now, this does not mean f multiplied by x. It means f of or f at x. This f is just the name of the function, and this x is just the independent variable, which we call the input of the function. And this 2x squared minus 5, right, the operations we do to the input value, are what we call the output of the function. So this f of x notation is just function notation that means the y value of the function, right? This f of x is equal to 2x squared minus 5, which is the output. And this f of x notation just names the function. Usually we use f, but it could be any letter. And then beside it is a place where the input goes when you're evaluating a function at a certain value of x. So for example, for this function, I know when x is -2, y is 3. We could show that using function notation by saying f at -2 is equal to 2 times the input value, which we've written here. We're inputting -2 for the x, so I'm going to replace the x in the equation with my input value of -2 squared minus 5. And then evaluating the output by doing 2 times negative 2 squared minus 5, I get an output, or y value, of 3. So this function notation, f of negative 2 equals 3, just means when x is negative 2, y is 3. This is saying the y value of the function, when the input, x value is negative 2, is equal to 3. Must know number 2, domain and range. Domain is the set of all possible input values that output a real value. So it's the set of all possible x values that you can sub into the function. Whereas the range is the set of all possible output values that a function can produce. So it's the set of all possible y values. And to demonstrate this, let's look at a function, f of x equals x squared plus 1. Let's start by making a graphical representation of this relationship between x and y, and then I'll show you how we can use both the equation and the graph to determine the domain and range. So to make the graph, it might be useful to start by making a table of values for this relationship. I'll choose x values between negative 2 and 2, and then use each of these x values as the inputs for x into my function. And then I'll be able to calculate the output value by doing x squared plus 1. So if I use negative 2 for my input value, f at negative 2 would equal negative 2 squared plus 1. So f of negative 2 would equal 5, which means when the input x is negative 2, the output value y is 5. And then inputting the remaining x values, I get these output values for y. And I'll plot all of those on my graph. And now I want to be able to analyze this graph and this equation to state both the domain and the range of my function. When determining the domain, I need to find the set of all possible input values that will output a real value. So I just want to figure out what values for x am I able to input for this x in this equation to be able to output a value for y. Well, you can input any real number for this x, and the output will be a real value, right? Any real number can be squared. So there would be no restrictions on what we could sub in for x. Or graphically, since we're interested in the possible x values that this function could have, we're just looking at graphically, how wide does this parabola get? Or horizontally, where does this function exist? And this parabola, it does continue forever. It's going to get infinitely wide. Right? When x is 9, let's say, we would be able to calculate a value for y. It would be really high. It would be at a y value of 82, but it does exist. And same in the negative direction. No matter how far you go in the negative direction, if you look up high enough, you would be able to see the graph of the parabola there. So we can say that the domain is just the set of all real numbers. And we write it like this. We say x is an element of the real number set. The real number set includes all rational and irrational numbers. Anything can be subbed in for this x, and you would be able to get a value for y. Or instead of writing domain in the set notation, you could write it as an interval of x values. You could say the domain is the interval of x values from negative infinity to positive infinity, which just means any x value between negative infinity and infinity is a valid input value for the x in our equation. And now for range, we would be looking for what are the possible output values we can get for our function. So what can x squared plus 1 equal? Well, because x squared is always going to be at least 0, when we add 1 to it, we're going to get a value that's at least 1. So the smallest y value we can actually get is 1. And we can see that on the graph, right? When thinking about the range, we would be thinking vertically, where does this function exist? Well, notice it's never below that point right there, which has a y value of 1. So vertically, it's always at 1, right? That point has a y value of 1, or above. It does go infinitely high. So to write the range inside of curly brackets, we say y could be any real number, so it's within the set of real numbers, given, we use a vertical line, y is greater than or equal to 1. Or writing this in interval notation, we could say the interval of y values would be from 1, right? The lowest y value is 1, and we want to include 1, so actually write a square bracket to include 1, comma, the highest y value it could have, well, it goes infinitely high, so it would go from 1 to infinity, and always a round bracket at infinity. number 3, common types of functions. You should be very familiar with the shapes of a few different common functions that you'll run into a lot. The first ones I'll show you are the shapes of the first 3 power functions. F of x equals x to the power of 1, which is just a linear relationship with a y-intercept of 0 and a slope of 1. F of x equals x squared, which is a quadratic, so it has a parabola shape. And next is f of x equals x cubed, which makes a bit of an S shape through the origin. So those are examples of power functions. And next, you should know the square root function, which is the function f of x equals the square root of x, where we calculate the output value y just by square rooting the input value x. Square root of 0 is 0, square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So those are a few points that I could graph. And for this function, it only exists at 0 or to the right. So the domain of this function, x has to be greater than or equal to 0. And that's because if I were to input a value of x less than 0, so if I put in a negative value for x, the square root of a negative number is not a real number. So it would not output a real value. Next, let me show you the graph of the rational function, the function f of x equals 1 over x. Now this function actually has 2 asymptotes. It has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. And we'll spend time later in this video talking more about asymptotes. But just for now, know that these are lines that the function is going to approach more and more closely, but never touch. And the graph of this 1 over x is actually broken into 2 branches, so its shape is called a hyperbola, and it looks like this. And now let's continue on. I want to show you 3 more graphs. You should know the shapes of common trig functions, exponential, and logarithmic functions. Starting with trig functions, we could look at the graph of f of x equals sine x, which is a sinusoidal wave that starts at 0 and then oscillates up and down between 1 and negative 1. And this is a periodic function, so the pattern of y values just repeats over and over and over again, creating this wave shape. And the graph of cos x looks similar. It's still this periodic wave that oscillates between negative 1 and 1. Notice it's just like a sine function that has been shifted to the left. And now let's look at both exponential and logarithmic functions, which are inverses of each other. So there's going to be relationships between them. An example exponential function could be f of x equals 2 to the power of x. For this function, any real number could be subbed in for x, so there's no restrictions on the domain, but the output value is always going to be bigger than 0, so there would be a horizontal asymptote at y equals 0. And this function 2 to the x, it grows very rapidly. It goes from 1 to 2 to 4, then to 8, and it just keeps on doubling as we move to the right. And as we move to the left, it would just keep getting cut in half, so we'll keep getting closer and closer to 0. So here's the graph of the exponential function 2 to the power of x, and you can see that it starts growing very rapidly as we move to the right. Whereas a logarithmic function, let's say f of x equals log base 2 of x, that's actually the inverse of the 2 to the x function, so it's the opposite. So it has a vertical asymptote at x equals 0, and it actually grows more and more slowly as we move to the right. So there's the graphs of 6 different types of functions where you should be very familiar with the shapes of their graphs. Must know number 4, transformations of functions. Let's say we have some parent function f of x. The graph of f of x could be transformed by stretching or compressing its graph, reflecting it, or shifting it. And we could do vertical transformations to the graph of f of x by applying operations to the whole output value of f of x. And if we wanted to do horizontal transformations, we would apply operations to the input value x. And we could give this new transformed function a name. I'll call it function g of x. So in this formula, it says that g of x is equal to a transformed version of f of x. These parameters, a, k, d, and c, transform the graph of f of x to give us our new transformed function, the function g of x. And we can get the graph of g of x from the graph of f of x by applying the following transformations. First off, the parameter c. That's what's being added to the output of the function. If c is greater than 0, the function shifts up. And if c is less than 0, the function shifts down. And next, the d value is the value that's being subtracted from the input of x. If the d value is positive, the function shifts right, and if d is negative, the function shifts left. Next, we'll look at the a value, which is what we multiply the output of the function by. If a is bigger than 1 or less than -1, it causes a vertical stretch by a factor of the absolute value of a. But if a is between -1 and 1, it causes a vertical compression by a factor of the absolute value of a. And if a is negative, that causes a vertical reflection. And let me make a bit of room. And lastly, we'll talk about the k value. The k value is being multiplied inside the input of the function. If k is bigger than 1 or less than -1, it's a horizontal compression by a factor of 1 over the absolute value of k. But if k is between -1 and 1, it's a horizontal stretch by 1 over the absolute value of k. And if k is less than 0, there's a horizontal reflection. So now that we have all of these rules, let me move them out of the way and we can try an example. This example says f of x equals x cubed, that's the parent function, and we want to graph the transformed function g of x, which is a transformed version of f of x. There are 3 transformations happening to it. We have an a value of 1/2, which would cause a vertical compression by a factor of 1/2, which means all of its y values are going to be cut in half. And then we have a d value of 2, right? The d value is what we're subtracting from x. Since we're subtracting a 2, the d value is 2, which means the function is going to shift right 2 units. So I would have to take all the points of f of x and shift them 2 to the right. So I would have to add 2 to all of the x coordinates. And then the c value is -1, which is going to shift the graph down 1 unit. So I would have to subtract 1 from the y coordinates of all of the points on the graph of f of x. And now let me do these transformations to the points of the parent function, x cubed. So I'll make a table of values for x cubed. Let me pick some x values for my parent function x cubed. I'll pick the x values between -2 and 2, and I can calculate the y values just by cubing them, right? F of x is equal to x cubed, so I just have to cube all of my x values. And let me plot that function on the graph that we have over here on the right. And now what we want to do is graph g of x, the transformed version of f of x. So I'm going to apply all of these transformations that we wrote down to these key points of our x cubed function. So I'll make a new table of values for g of x, where the transformations that are happening to x is I have to add 2 to shift it to the right, and to the y's, I have to cut them in half to vertically compress it by a factor of 1/2, and then I have to subtract 1 to shift it down 1. So I'll take all of the x values from my parent function and sub them into this little equation that I've made. So I basically just have to add 2 to all of these x values to get my new x values. And now I have to take all of these y values and then cut them in half and subtract 1. Well, half of -8 is -4, and subtract 1 is -5. And I can do that for all of the points. And now I can plot these points to get the graph of my transformed g of x function. And then I'll go ahead and connect them. And there we have the graph of g of x, which is a transformed version of f of x. Must know number 5, the inverse of a function. Let's start with the notation. The inverse of f of x is written like this, where this -1 is not an exponent. It doesn't mean to the power of -1. It's not the reciprocal of f of x. It's the inverse of f of x, where an inverse function reverses another function. For example, if f of a equals b, for an inverse function, the inverse of f at b would actually equal a. Or another way of stating that is that the inverse at f of x is equal to x. And both of these are just different ways of saying the same thing. If I take the output of f of x and I sub it as the input into the inverse function, that inverse function actually outputs to me the original input, x, on the original function. So it just undoes all of the operations that f of x does to x to return just the x value. And if we're to compare the graphs of f of x and the inverse of f of x, the inverse of f of x is just reflected across the line y equals x. And the graph of f of x and its inverse actually share all of the same points, but their x and y coordinates are reversed. And now let me demonstrate all of these properties to you with an example. The example says, if f of x equals 2 to the power of x, let's graph